Hi, yes, my name is Courtney Crawford. I'm a postdoc at the University of Sydney, and today I'm going to talk to you about the dust properties of R Coronae Borealis variables. This is going to be predominantly an observational based talk. I want to start out by shouting out my research collaborators because without them, my work would not be possible. So every single person on the screen is immensely valuable to me. So the R Coronae Borealis stars, which you just heard about, I'm lucky that I don't have to spend the time explaining this too much, but I'll give you my one-sentence summary, which is that the R Coronae Borealis stars are a rare, dusty, low-mass, supergiant star. They are also a subclass of what we call the hydrogen-deficient carbon stars, which are potentially formed via double white dwarf mergers, as you just heard. There's also a subclass of these HDC stars that do not form dust. But today I'm going to talk about the dusty ones, so just pretend those don't exist. What they're known for, and what Mark talked about, is that they're known for their irregular dust declines, up to 9 magnitudes in the V band. So here I have the light curve of 28 years from AAVSO, just a snippet of the R Coronae Borealis, the prototype light curve, where on the y-axis you can see that at its brightest, it's at about 6 mag, and at its record dimmest, it's at about 15 mag. That's 9 magnitudes in V. What you also might notice is that it has some variability up at max light. That might be pulsations, question mark. But what you also will notice is that each of these declines has different depths. It is asymmetric, so we tend to have sharp downs, slow rise up. You also notice that in general, they are not periodic. So they're quite interesting. And the image we have in our head, our toy model, if you will, is this kind of image. So since they're supergiant stars, we believe they rotate quite slowly. And what we think happens is that there's some form of puff, if you will, a little cloud of dust that forms in our line of sight. And then as it moves away, it begins to obscure more of the star, and eventually covers most of the star. And then as it moves even further away, it gets optically thin, and we can start to see through and see the photosphere again. So here's just a GIF that I drew by hand to try to show you what I mean by this. But the problem is that what we need to do is actually look at declines in stars to try to refine this dust model, because we are still working with a toy model at this point. And in my opinion, this is because up until 2018, we only knew of about 30 of these stars. And recently, we've increased that number up to about 200 that we know of due to the work of Patrick Tisserand. And so large-scale studies of R Coronae declines have not been done in the previous. Only the brightest stars historically have been studied, so R Coronae itself and a few other stars, especially with data like AAVSO. So what we really want to do is take the properties of this light curve here and try to inform our model so that one day we can have a model of the dust itself. So the first thing we did was collected a bunch of photometric data. We are very lucky in that R Coronae are some of the most observed variable stars on the AAVSO. Here's the light curve of R Coronae Borealis itself. It's 227 years long. And you can see just the absolute wealth of information we have. Every gray point is a visual measurement by eye. It's a by eye measurement. And the blue points here at the end are V-band measurements, which only come more recently. If you're curious, the dash plates would live right in here. They're just not on AAVSO yet, but we are working on that. So here's what R Coronae looks like. It's the famous one. Everyone knows this star. But here's a different star. And in this type of star, we have all sorts of other different information we collect. And in fact, we go and collect data from 12 different photometric surveys: ASAS-3, MACHO, EROS-2, OGLE-3, OGLE-4, Gaia, if available, Atlas, ASAS-SN, ZTF, KMTNet, NEOWISE, and Gattini. Those last two are infrared surveys, so we do have that information, but I'm not going to talk about it today because it's a little bit harder to deal with, but the optical photometric information we're really interested in. So here's a light curve of AOHER, where you can see all this different data that we have. And this was collected by my collaborator, Jamie Soon, who actually has all of this data on a monitoring website. So if you want to go in, you can look and see if your favorite R Coronae is in decline today. But we have all this lovely information, and you can see that as you combine all of these different light curves, you really start to get an idea of what the star is actually doing over longer timescales as some photometric surveys come and go. And so then what we've done now, or what I've done, is to use all of the available data and go in and just locate every decline. Locate the onsets and the ends of every observed decline for all of the roughly 200 known R Coronae stars. By definition, we choose declines to be greater than 1 mag. This is to avoid pulsations at maximum light. And then in general, what we do for the rest of this talk that I'll talk about is we're going to analyze overall decline statistics. So here's for AO-HER, the 6 declines that we would measure. And a couple of things to note is that we don't measure the start for this one, we don't measure the end for this one, and these which occur inside of a decline, I call nested declines. And a lot of times I will remove those for various reasons. So here, what I want to get across to you is that every R Coronae is different. And here's an example of 3 stars which are bright, which have almost no declines over long periods of time. We have some stars which have lots of events. They're just constantly going up and down in unpredictable manners. But we have some stars which are just always at minimum. So they just sit at the bottom and then occasionally they rise up a little bit, but we aren't convinced that we ever actually see them at maximum light. So what we need to do is define some statistics for how we actually want to look at this. And the easiest one to define, the first one I'll talk about, is the decline frequency. That's the number of declines per year that we observe it. So for AO-HER here, we have 6 observed declines. Our baseline of observation is about just about 9 years. We just we divide those and we get about, for this star, 0.66 declines per year. And we do this for every single star. So what does that look like? What we find from this is that cooler stars have more frequent declines. To many of you, this is probably not surprising. In fact, it's probably intuitive. Cold stars have more dust, maybe makes sense. So what I have here is declines per year on the Y. I have the HDC class here on the bottom. This is a spectral classification system that I made for my PhD thesis, where the warmest stars are 0s and the coolest stars are 7s. By warmest, I mean about 8,000 Kelvin-ish, and by coolest, I mean about 4,000 Kelvin-ish. And so you can see that for these coldest classes, we tend to have this increase in the frequency of declines per year. But we still have declines up at these warm stars, which is quite interesting as well. You might be like, what the heck is that thing? These are the DY Persei. I include them in this analysis, but I haven't introduced them yet. There is a lot of recent, maybe not a lot, there's a few papers in recent literature suggesting that the DY Persei, and specifically DY Persei, the prototype, might just be a cool R Coronae, roughly around 3,500 Kelvin. So there's some recent literature suggesting this, but ultimately they're not well studied and we don't really know what they are too much. So I include them here because they do have dust declines, and you can see that they look quite different, and they don't follow the trend that the cool R Coronae do, which maybe gives us some information in the future on what they are. The second decline statistic that I've measured here is the percentage of observed time spent in declines. This has to do with the decline lengths. This is the length of the time that it spends in decline. You just divide that by the baseline. So for this star, that's about 42% of its time spent in decline. What does that one look like? Looks quite similar. Cooler stars also spend more of their observed time in decline. You can imagine these two are related. I'll get there. But we do see the same trend here, where maybe it even looks a little bit more linear, where this part is a bit less flat. I'll ask you to keep in mind that this plot in particular has a maximum on the y-axis, which is not 100. That is because stars above 90% obscuration likely have no spectral type, as we have to observe them at max light to get a spectrum for a spectral type. But if you plot the relation of these two, those stars come back, you have your 100% in decline stars. And these two are related, the percent of time in decline and the frequency of declines, by an average decline length. So the average of the average decline lengths, which is a weird unit, is about 94% of a year. So most R Coronae declines on average are about a year long. Of course, there's still significant scatter around this relation, but that does give us a really interesting number to use here. The third decline statistic I want to talk about is the delay times, or AKA the waiting times, if you're familiar with that term. This was inspired by solar flare work. I just took a lot of inspiration on what exactly solar flare people were doing. So what this is you take the onset times of each of your decline, you take a pairwise difference, and then you sort them, you have a cumulative distribution of delay times or wait times. So this is only done, I only did this for 2 stars that I'm going to show today. That's because they have very long baselines, so 227 and 115 years. And the other important thing to keep in mind is that these are also very well sampled. So if you have gaps in your data, then your wait time distribution is probably not very good. So what this is a reversed cumulative distribution of the wait times for SU tau and R Coronae itself. And here you can see that the data are in blue points. This orange line here is just a straight up Poisson distribution of what that would look like. And this lambda is not a fit. This lambda is the decline frequency. So the rate of this Poisson distribution is the decline frequency that we measure just from counting. So they do follow roughly a solar flare, roughly a Poisson distribution, which is similar to what they see in solar flares. And what this might mean is that this is some kind of avalanche or cascade-like dust formation model. As Mark mentioned, we don't necessarily know how the dust is forming. There's lots of different ways that this could be forming. But maybe this is something that could help potential modelers in the future to figure that out. The last one I want to talk about is the slopes of decline onsets. So what I mean here is I want to go fit a line from the top to the bottom of each decline. So for example, at this first one, since I don't have the onset, I would cut that out. And I also don't include nested declines here because I specifically want to know about the slope from top to bottom, so from maximum, because it's possible that this dust cloud was formed inside of another one. And so I really don't size and perhaps velocity play into the speed at which you're downward. And so I've measured this for 6 R Coronae and then DY per. And these are all stars that have AAVSO data. So again, I want really long baselines because I specifically want to have the most declines as possible. So these are the ones where we measure the most declines. You can see that each star has a different distribution of decline slopes. This unit here is % blocked per day. It's kind of a weird unit, but 0.01 means that the star's flux is going down 1% per day. So if you want to get to 100% obscuration and you're at, say, 0.2, right, then you need 50 days to get to minimum, right? So that's the sort of timescale we're talking about. So all the R Coronae that I've measured look like they have slightly different distributions, but in roughly the same area. But what you might also notice yet again is that DY per looks different, where DY per has much smaller slopes compared to the others. And that means that its declines are going down slower. They also are shorter, fun fact, and they are a bit more symmetric than observed R Coronae declines. So maybe there really is something different going on there. So just to summarize, I've told you a lot of things. First off, the main thing that we found is that DY pers look like they have super different dust properties than R Coronae. Maybe you've never heard of either of those stars before and you're like, I don't care. That's fine, but we actually have just no idea why this would be. DY pers are not well studied. I think there's maybe like, I can think of 10 tops papers about these stars, and most of them are about DY Persei itself. So we really just don't understand why that would be. We also find that cooler R Coronae stars produce dust more often. This doesn't still explain how a star at 8,000 Kelvin can form dust near its surface. So these are measured to be at about 2 stellar radii. We also find potentially that dust production events might be Poisson distributed, which could point us in some sort of direction for our future dust formation models. And we see a range of dust decline slopes, which might point to a range of potential dust velocities and initial dust cloud sizes. So with that, I will thank you. I have some options up here for things we can chat about or collaborate about if you want to take the bait. But otherwise, please email me or contact me on Slack. Thank you.
Hi, thanks for the great talk. You've got I guess, an abundance of light curves in all different bands. I was wondering if you could learn anything interesting from maybe the differences in the slopes in each of those bands or something like that.
The common one that people talk about is the depths, right? So if I go back to AOHER, where's the closest AOHER light curve, please? Okay. You might even notice here in Gaia, right, that the depths are different. And that does tell you about the color response of the dust, which does tell you about the contents of the dust. That is something that we are planning to work on. I just haven't done it yet.
Just very quickly. So the velocities at which the dust clouds may be ejected should be calculable. If there's going to be some kind of radiation pressure, or if the wind was already carrying, it's going to be a escape velocity.
Yep.
So those numbers consistent with the fading we see, or the fading meaning the returning to maximum.
Yeah. So Jeff has some models on that, on the return back up to the velocity, and they are consistent. I don't have numbers off the top of my head, but what I do also know is that I have a cool backup slide. I love backup slides, you guys, so I have too many, but I have one that's really cool. Maybe? Please? From Ed Montiel's PhD thesis, where he looked at Herschel data, Herschel images. Sorry, guys, I'm telling you, I really like backup slides. It's not even on there anymore, is it? Okay, I deleted it. That's funny. So anyways, there it is. Wow. Okay, so Ed Montiel, for his PhD thesis, did look at Herschel data where he looked at the dust around here and was able to measure some velocities, and he measured them to be about 400 kilometers per second.
Okay, thank you. I really enjoyed the talk.
Thank you.
I have two questions. The first is why the slope of the declines can represent the dust clouds of the size of the dust clouds. I can only understand the velocity.
So it's more like the initial size, right? So if you're using a geometric argument, I did this on the back of the envelope, so it could be wrong. But like if you have an initial dust cloud size, then as it moves towards you, it expands. That expansion is probably understood, but you need to know that initial size and the velocity to get the actual current size that you see it at. Does that make sense?
Yeah, so maybe I think something like equivalent width in their spectral analysis of the light curves, you can convert it to maybe a better representative for the size of the dust cloud.
Equivalent with how?
Equivalent width, yeah, because you can measure the depth of the decline and also to integrate the area of this decline. Yeah, maybe, I don't know. The second question is if it is possible for us to study the mass loss rate of the stars through the light variations in your analysis.
The mass loss rates from the what?
From the light curves, from the declines.
Maybe. Yeah. It's entirely possible. This is like relatively early stages, and there's a lot of stuff that we have planned in the future. It's just ultimately right now, what we're trying to do is get the numbers, and then we start thinking about models in future work. So I definitely think we can, and I think that's on the plate. We just haven't done it yet.
Yeah, I'm looking forward to it. Thank you very much.
Thanks, Courtney, for your great talk. This is not really a question, it's just a comment. I'd like to talk to you about abundances in our core bore stars and S process. So maybe I can find you later.
I have lots of thoughts.
I also have a question.
Yeah.
Why are you only looking to the decline of the event and not when it comes back to maximum light? You know, that also.
I think one, maybe, I'm trying to show you one specific example, which is this famous decline from R Coronae, the big one. You can see that it actually has many little things going on inside of it. So it tends to be actually a lot more complicated. But for some of the smaller ones, like if we can be convinced that it's just one cloud, we do that a little bit. I just am not familiar with that process myself. Yeah, I know Jeff has done it, and it's in the works.
Thank you so much for a nice talk. I was wondering if there's any correlation between the big dips or the frequency of the dips and the pulsation period of the low amplitude pulsations.
That is a great question. I would love to tell you the answer. Ultimately, studying the pulsations is really difficult. And that is because of the declines. So I don't have an answer for you yet, but it is something that I am very interested in and something that I am working on imminently.
Okay, thank you.